All right. So let's find the for any point t. Okay. For example, this is my x1 axis. This is my t axis. And the value I have, for example, non-zero value between A and B. Okay, the Q x is not zero within AB. Okay? So that means all others are zero, have no influence on. So the value of point A, so this is what we call okay. So this is my zone of influence by value at x1 equal to A, right? And this will be the zone were influenced by me, by the information SB and boundary. So here we have an intersection point. And this line of equation is x minus alpha t equal to b. Okay? Equal to b. And this line will be x plus alpha t equal to b. And this equation will be x forward, right? Minus alpha t equal to A. So this will be backward, so x plus alpha t equal to A. 1. Okay? Right? Because on this line at t equal to 0, x1 equal to b. On this equation, when t equal to 0, x1 equal to A. On this equation, when t equal to 0, x1 equal to b. On this equation, when t equal to 0, x1 equal to A. So the full equation. Okay? Then you can solve. You can solve this interaction point at where? You can solve it. Okay? I don't want to solve. You can solve at this equal to half A plus B for x1, this point. And the t, and it's t. The t is equal to b minus a over 2 alpha. Okay? So this is a critical line interval. So for the t, for t larger than b minus a divided by 2 alpha, I can the value I can divide the interval for 5 interval. Interval 1, interval 2, interval 3, interval 4, interval 5. Okay, 5 interval. Okay, 5 interval. Yeah. Okay. And remember, in this problem, I have only non-zero value here. So here in zone 1, all thing I will be influenced by the value is here. The zone 1 is initial value depends on here, all are 0, so no displacement. Same thing at here. For the point at x5, 0.5, and all the information, it depends, all are 0. Like here, the point, only any point here, the only values at equal A. But for the interval at here, any point here, it will have information on this wall, but only A to this value. All others are 0. Right? So from this concept, we can get the result from this initial value about velocity and to get the solution of this one. Okay? So that means the integral for any x1 value, it depends on the point on each interval, and you will look at the interval of interest. Okay? Yeah. So you have different x1 t value at this 5 interval at any point. Yeah. Okay. So after you got this concept, so that's why this is very important. How do we get this value? So the analysis will divide by 2 parts. One is for the t smaller than b minus a divided by 2 alpha, and t bigger than 2 alpha. So our solution will depend. We'll look at these 2 kind of a time value. Right? Certainly, this is value to 0. This is what I was interested in. And another is that from t larger than this value. After this value, we have some different solution. Okay? Yeah, now it's already very, a little bit, how to say, complicated or more profound theory. Okay, this is a wave propagation. We just start 1D wave propagation. Now let's look at the detail. Okay. Remember, my solution is the Allenberg. Today, I'm always talking about the Allenberg solution. Okay, the displacement solution at x1 anytime t, u1 is equal to half the initial displacement at the boundary point x plus alpha t and the initial displacement at x minus alpha t, these 2 points. Maybe better this minus and this plus, okay? And initial velocity integrated about the x range x1 minus alpha t to x1 plus alpha t. And the initial velocity information inside the interval. All right? So that means in this domain, for any point, okay, it will integrate. This is this is x1 t. So this will be x1 plus alpha t, right? And this point will be x1 minus alpha t. So I need all the information inside this interval, but some only this part was effective, okay? And these are 0. If this point locating this point, and its dependence all are 0, no result, okay? So the interval will relate to the value on this interval, okay? All right. So let's look at, okay? So the u1 xt is 0 for the region 1 and 5. Okay, so this is region 1, region 2, region 3, region 4, region 5. Okay, so we have this 5 region. For 1 and 5, because all the point independent is a domain of the dependence, the value all are 0. So displacement, because all are 0, so the displacement are 0. Okay. For the in the region 2, the displacement u1 x1 t equal to 1 over alpha for any point here is dependent. There is for a to x1 plus alpha t. So it's from from a to x1 plus alpha t and q s ds my integration. Okay. For any point in here, this domain of dependence is from a to x1 plus alpha t. Okay. In domain 3, inside here, it will cover a to b. So the third case, in the region 3, my displacement u1 x1 t will equal to 1 or 2 alpha is valued a to b qs ds. Okay, only this one. And in 4, for the 4, so this will be x1 minus alpha t to b. So in the region 4, my displacement solution will depend on the velocity information from x minus x1 minus alpha t to b qs ds. Okay, so that's my solution. Depends on your value q function. Okay. If I give you okay, this is a concept. Now if okay, so this is only for the case for t larger than b minus a divided by 2 alpha. And you also can do the homework okay? So homework. Discuss for the cases t larger than 0, smaller than b minus a over 2 alpha. Then this range. You still have 5 zone. I think so. Okay, you can have 5 zone. Okay. Right? You can have a zone here. And right. So this will be one zone. Okay. And this will be one zone. This will be one zone. This will be one zone. Okay, you have sort of the one zone 1, 2, 3, 4, 5. But be careful for the So for zone 2, it will what? Zone 2 will from A to x1 plus of 2. For zone 2, okay. And for zone 3, probably will be different. Okay. For zone 3, it will have different value. So zone 3, here is A to B. But for the time less than this value, zone 3, the value will be x minus alpha t to x plus alpha t. Okay? Will be changed different. Okay? Yeah, be careful. Okay, so this is for the initial velocity, right? Yeah, if I give you a distribution about the initial velocity, like an initial function, maybe triangle or whatever, okay? Yeah. You can substitute this integral and get some value, okay? So depends on how complicated your given distribution function is. But for this kind of triangle or discontinuity, you need to use a heavy side or something else to do the integration. All right? Yeah. Okay. Depends on, but the interval, you have to be careful about the interval. Yeah. Okay, go home, do the homework. It's homework. I will change it, okay? That one easy, because I already gave you an answer, but let's try to do a problem. Homework. Homework number what? Number 3 or number 4? 第几个？啊？第二个 ，OK。Number 2。The Px equal to 0 and the Qx1 equal to U0 initial velocity x1 0 is like this. Okay, let's do this way. This is 2. Okay. And height is Q. Let me give you a delta right here. Q delta. No. Give you this height. We call the V0. Okay, and this is the interval delta. I give you this shape. Okay, and and this is at A, and this is at B. Okay, and this is velocity distribution. Okay, so plot the displacement distribution at time t equal to 1/4 alpha, 4 alpha, 2 alpha, alpha, 1/alpha, okay. 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 This time, product. Show me the distribution. Yeah, I give you this more general equation, huh? So in the future, if you write computer program, just input the A, B, delta, V0, you can see the propagation of this signal. Okay. Yeah, you have to first write out the equation by Heaviside function. Okay. Then do the integration. How to do Heaviside function integration? Dependent range, right? For the value larger than that would be equal to 1. Okay. Okay. All right, try to do it. Okay. Yeah, well, already give you some